Welcome to this video on quantum chemistry, wave functions, and molecular orbitals. In this video, we will explore the fascinating world of quantum chemistry and delve into the concepts of wave functions and molecular orbitals. Quantum chemistry is a branch of chemistry that studies the behavior of atoms and molecules using the principles of quantum mechanics. It is a complex field that involves the use of mathematical equations and models to understand the behavior of matter at the atomic and molecular level. At the heart of quantum chemistry lies the concept of wave functions. A wave function is a mathematical function that describes the behavior of a particle in space and time. It provides information about the probability of finding a particle in a particular location at a particular time. In quantum mechanics, particles are described as waves, and wave functions are used to describe the behavior of these waves. The wave function of a particle is a complex mathematical equation that contains information about the particle's position, momentum, and energy. Molecular orbitals are another important concept in quantum chemistry. A molecular orbital is a mathematical function that describes the behavior of electrons in a molecule. It provides information about the probability of finding an electron in a particular location in the molecule. In the next segment, we will explore the concept of wave functions in more detail and see how they are used to describe the behavior of particles in quantum mechanics. In quantum mechanics, wave functions are used to describe the behavior of particles such as electrons, protons, and neutrons. The wave function of a particle provides information about the probability of finding the particle in a particular location at a particular time. The wave function of a particle is represented by the Greek letter psi. The wave function is a complex mathematical equation that contains information about the particle's position, momentum, and energy. The wave function of a particle is not directly observable. Instead, it is used to calculate the probability of finding the particle in a particular location. The probability of finding a particle in a particular location is given by the square of the wave function. The wave function of a particle can be described by a set of quantum numbers. These quantum numbers provide information about the energy, angular momentum, and magnetic moment of a particle. The Stinger equation is a fundamental equation in quantum mechanics that describes the behavior of particles in terms of their wave function. The Stinger equation is a complex mathematical equation that describes the time evolution of a wave function of a particle. In the next segment, we will explore the concept of molecular orbitals and see how they are related to wave functions. Molecular orbitals are a key concept in quantum chemistry. A molecular orbital is a mathematical function that describes the behavior of electrons in a molecule. It provides information about the probability of finding an electron in a particular location in the molecule. Molecular orbitals are formed by the combination of atomic orbitals. Atomic orbitals are the wave functions that describe the behavior of electrons in an atom. When atoms combine to form a molecule, their atomic orbitals combine to form molecular orbitals. Molecular orbitals can be classified as bonding or antibonding orbitals. Bonding orbitals are formed by the constructive interference of atomic orbitals, while antibonding orbitals are formed by the destructive interference of atomic orbitals. Bonding orbitals are lower in energy than the atomic orbitals from which they are formed, while antibonding orbitals are higher in energy. The number of bonding and antibonding orbitals in a molecule depends on the number of atoms and the type of bonding between them. The electronic structure of a molecule can be described by its molecular orbitals. The distribution of electrons in the molecular orbitals determines the chemical and physical properties of the molecule. In the next segment, we will explore the relationship between wave functions and molecular orbitals and see how they are used to describe the behavior of molecules in quantum chemistry. Wave functions and molecular orbitals are essential tools in quantum chemistry. They are used to describe the behavior of particles and molecules at the atomic and molecular level. In quantum chemistry, wave functions are used to describe the behavior of particles such as electrons, protons, and neutrons. The wave function of a particle provides information about the probability of finding the particle in a particular location at a particular time. Molecular orbitals are formed by the combination of atomic orbitals. They provide information about the distribution of electrons in a molecule and determine the chemical and physical properties of the molecule. The wave function of a molecule is a complex mathematical equation that describes the behavior of the electrons in a molecule. The wave function of a molecule can be expressed as a linear combination of the molecular orbitals. The Stinger equation is used to calculate the wave function of a molecule. The Stinger equation is a complex mathematical equation that describes the time evolution of the wave function of a particle. In quantum chemistry, wave functions and molecular orbitals are used to calculate the electronic structure of molecules. The electronic structure of a molecule determines its chemical and physical properties. In the next segment, we will explore the applications of quantum chemistry in various fields such as materials science, drug design, and energy research. Quantum chemistry has numerous applications in various fields such as materials science, drug design, and energy research. In materials science, quantum chemistry is used to understand the properties of materials at the atomic and molecular level. It is used to design new materials with specific properties such as strength, conductivity, and durability. In drug design, quantum chemistry is used to study the interactions between drugs and their target molecules. It is used to design new drugs with specific properties such as efficacy, selectivity, and safety. In energy research, quantum chemistry is used to study the behavior of molecules involved in energy production and storage. It is used to design new materials for energy storage and to optimize the efficiency of energy production processes. Quantum chemistry is also used in environmental science to study the behavior of pollutants and their interactions with the environment. It is used to design new materials for pollution control and to understand the impact of pollutants on the environment. In conclusion, quantum chemistry is a fascinating field that has numerous applications in various fields. The concepts of wave functions and molecular orbitals are essential tools in quantum chemistry that are used to describe the behavior of particles and molecules at the atomic and molecular level. Thank you for watching this video on quantum chemistry, wave functions, and molecular orbitals.